bigger than 1. So this is just an example. And actually there are infinitely many knots which doesn't satisfy this formula. So now I want to give you a sketch proof of the lemma. Okay, I have enough time. Okay. So if you have any questions, please feel free to ask me. Then sketch proof. Sketch. And we have these facts. Facts number 1, due to clock, gamma of k is equal to 1 if and only if k is a 2q cable knot. And here q is an odd number. And fact 2, the knot signature is a concordance invariant. Namely, if k0 is concordant to k1, then we have sigma of k0 is equal to sigma of k1. And we have fact 3. And according to Fox and Milner, so if k0 is concordant to k1, and then the Alexander polynomial is of such form, Alexander polynomial of k0 times Alexander polynomial of k1 is such a ft equal times ft inverse. There exists some polynomial ft with f1 is equal to 1. And by replacing t with -1, it follows that the determinant of k0 times determinant of k1 is equal to, is a square. So here you can see this, the L in our lemma comes from here. Okay. So now, assume that gamma c of k and p is equal to 1. Then we know that then there exists k prime according to k and p with gamma of k prime is equal to 1. So now we can use the facts listed here. And we know that k prime is a 2q cable knot. And sigma of k prime is equal to sigma of k and p. And also determinant of k and p times determinant of k prime is a square, odd square. And so now we only need to calculate the signature and also determinant, right? And to calculate the signature, there is a formula given by Gordon and Lisman. I will just write it here. So K is a knot, and there's a sphere, surface bounding knot K, and we can associate this surface Garrett's matrix, and this Garrett's matrix can be calculated. So if given a generator system of the first homology group of the surface, and GF is actually this kind of symmetric matrix, This is tau aj. And tau aj means how to say? Tau aj is one cycle in S3 minus F obtained by pushing of 2aj. And then we know that sigma of k is the signature of this Gauss matrix plus a correction form, and this correction form is given by the normal Euler number, which is introduced in Sato's talk. So I'm not going to introduce here. And I just tell you how to calculate. Ef is linking k and k prime. Here, k prime is the intersection between the surface F and the boundary of the neighborhood of k. Okay. So now we have everything, I think, and let's go back to here. So now we have this surface here, right? This is a Seifert surface. And we can take a generator system. So in this way, this is A, and this is B. And we can calculate the Gauss matrix of this surface, and it is a 2 by 2 matrix. And then we can know and also this is an orthogonal surface, right? And the normal number is 0. And then we can calculate the signature of this knot. Actually, it's the signature of this Gauss matrix. And so we know that sigma of k, sorry. I'll write here. Sigma of k and p is 0 or 2. And on the other hand, we know that k prime is a 2-cube cable knot. And we know we can calculate by using Gordon-Liesman's lemma. We know that k prime is sine of q minus q. And then, so this gives us a restriction on number q, right? And we know that q is 1 or 3. And also we can calculate the determinant. The determinant of k prime is actually, so since, how to say this, k prime has a one-dimensional Gauss matrix given by q. So this is the Gauss matrix of k prime. And then the determinant of it is just the absolute value of q. And determinant of k and p is the determinant of this 2 by 2 Gauss matrix, and it is 8m minus p squared. And then, so by these formulas, and also this fact, we get the proof of the lemma. We have that formula. And it's done.
Are there any questions or comments? Okay, let's thank the speaker again.